welcome back to the class of Calculus 3. This time we are moving to section 4.7 about the maxima and the minima of function of multi-variables. Indeed, we are only working on function of two variables. Okay, so if you remember the topic of chapter 4, it is about the function of two variables and the three variables. And we have discussions on partial derivatives, directional derivatives, gradients, tangent planes, those things. And also in this section, we will continue work with derivatives and an application of partial derivatives about maximums and minimums of a function of two variables. Maybe before I go further, I can show you a graph quickly so you got some idea what kind of topic to expect. Remember, the function of two variables, the graph of function of two variables in a three-dimensional space is a surface. Okay, these colored things are the surfaces. Surface like this, surface like that, or surface like the other one. And indeed, I say mostly we just want to point out this surface, the special thing of this surface. It's a saddle-shaped surface. And particularly if you take a closer look, the surface, the point right here, I think this is the center of the saddle. Okay, because if you look closely from one direction, I'm trying to move my mouse around to show you the shape I'm talking about. We're kind of having parabola opening upward. It is a parabola opening upward. And then the other direction, we may have parabola opening downward. So at the point, if you look at this direction when the parabola opens upward, looks like we have a minimum. But the other direction, when the parabola is opening downward, looks like we may have a maximum, the point on the top. But as you can tell, overall, a point on the surface cannot just be sometimes maximum, sometimes minimum. So based on this observation, we are having a saddle point. This is a saddle-shaped surface, and in the center, there's a saddle point here. And also the other two cases, I guess, a lot easier to follow. And we are having 2 points. They are kind of in the top position on each part of the surface. So they are called the local maxima. And this is the case. We are having 2 points in a relatively lower position. So each, it is called as a local minimum. And then the question is, given a formula for the function of two variables, how do we really know if it has a minima or maxima or saddle kind of thing? So to get us started, we will first define a new concept, a critical point. A critical point for a function of two variables. It is a point where both partial derivatives equal to 0. Two partial derivatives, okay? It is required both partial derivatives equal to 0. Or you could have this case, either the partial derivative is not defined. That is a critical point. And also for our consideration, mostly we are just going to consider the case when partial derivatives are defined and both partial derivatives are 0. Okay, that is a critical point. Remember in calculus 1, we know a function may have a maximum or minimum or neither at a critical point. Similar situation for function of two variables, but it's more complicated. So accordingly, in order to determine maximum, minimum, or saddle point, we needed to use this second derivative test. This is for the function of two variables. And first, we do assume we already got a critical point, x naught, y naught. It is a critical point. And then what you need to consider here is you are going to create a D. This D really is determinant. See, this is determinant of 2 by 2 matrix, right? That is number, that is also number. So D really is the determinant. And also, if you like, you can consider this as a formula. This formula really is a calculator determinant, okay? Calculator determinant. And determinant arranged according to the second order partial derivatives. Remember, there are 4 second order partial derivatives, right? Namely fxx, fxy, fyx, fyy. And also, I hope you still remember, because of the Clairaut theorem, fxy, fyx, they are the same. So we have this as the perfect square over here, because fxy, fyx, they are just the same. Okay, this is how we define D. And then to decide if we got a maximum, minimum, or saddle point, we look at those 4 cases. If the case you defined, certainly the D is defined at a critical point. At different critical points, there are different Ds. Say we look at one critical point, if the D is positive, and if we know the second order partial derivative with respect to x is positive, then what we can say here is f has a local minima at that critical point. And if D is positive and the second order partial derivative is negative, then we say the function has a local maxima, or really not we say the function must have a local maxima at that critical point. And then another small issue, how do we really remember minimum or maximum? I want to say this is calculus 3. I suppose you know calculus 1 very well. In calculus 1, we know the second order partial derivative would indicate the concavity. Second order partial derivative is positive, which means the graph of the function opens upward, like in this case. Overall, the graph of the function opens upward. So accordingly, you may have the critical point in a lower position. So that is a local minimum. And also, in the second case, second order derivative, it is negative, which means the concavity is opening downward. So accordingly, you may have a critical point at the top, on a high position. So accordingly, it is maximum. And certainly, you do need to check the value of D, okay, the uppercase D. The uppercase D roughly can be considered as the determinant of the second order partial derivatives. It's a 2x2 square matrix. Okay, D is positive, we possibly could have maximum or minimum. And then when D is negative, D could be negative. D is negative, actually it is the third case, when you're having a saddle point. When you're having a saddle point, which means the point at this critical point, it is not a maximum or minimum. And also this D could be 0. Well, at this moment, I just want to say the D is 0. We cannot make any conclusion. The test, it is inconclusive. Mostly for our class purpose, we are just going to consider those first 3 cases. That is the so-called second derivative test. It really will answer the question about the maximums and minimums for function of 2 variables. Okay, let's take a look. Another example. This is the example from the textbook. It is checkpoint 4.35. It is find out the local extrema of this function of 2 variables. And the extrema, it is a maximum or minimum. Okay, also could be a saddle point. So first, we find out the critical points. Really, that's all about the second order derivative test. And certainly, we cannot jump to the second order derivative. We are going to start from the first order derivative. And we set both first partial order derivatives as 0. Because this is how a critical point is defined. And then specifically in this case, I'm seeing x equals 4y from f sub y, right? X equals 4y from f sub y. And then I substitute this result back into f sub x. X is replaced with 4y. And then I did some necessary simplification. And basically I'm seeing 48, 2, and 6, these are all even numbers, so it would be easier if we can reduce or simplify those numbers. I divide the entire equation by number 2. I got a new quadratic equation in terms of y. And this quadratic equation can be factored into this fashion. 3y minus 1, 8y plus 3. It should be alright, right? So which means there are two solutions for y. Y equals 1/3. Don't forget x equals 4y. So when y equals 1/3, x equals 4/3. Okay. And the second solution is y equals negative 8/3. Again, because x equals 4y, so you multiply this y value by 4. That turns to be negative 32/3. So I'm saying for this part of the calculation, we got two critical points. And then each critical point could be a maximum, minimum, or neither. So we will have to look at each critical point separately. This step 2 related according to the second derivative test. We calculate the second order partial derivatives. Namely, there are 4 of them, so I got 4 of them. And also, you may want to know, because of Clairaut's theorem, it is always true. fxy, fyx are the same. Okay, and then I calculate the determinant. It's a d for each critical point. I consider 4/3 and 1/3 first. So this is how d is arranged. And indeed, that's the determinant of 2 by 2. So indeed, this is the formula. And then I plug in at the critical point. I'm considering this critical point here. X naught, Y naught. Okay, it's this ordered pair. So I plug in numbers and fxx, fyy, replace x with 4/3, right? And fyy, actually that's a constant. Then fxy still that's a constant. What I'm seeing here is, well, actually, in this case, the d, this is negative minus negative. It is still less than 0, right? This d, it is negative, which really means we really don't have to worry too much. At this critical point, it is a saddle point, which means it's really not a maximum or minimum at all. So far, so good. We're talking about the second order derivative test to find out the local maximums and the local minimums for function of 2 variables. And so far, we got a saddle point. Remember, we are having 2 critical points, right? Saddle point, it is just 1 critical point. So we look at the second critical point, negative 32/3 and negative 8/3. Accordingly, I calculate the determinant again. Formula-wise, it's the same formula. I just copy and paste it. But anyway, there are different numbers, right? So fxx, fyy, fxx as calculated over here. That's 6 times whatever the x value is. Okay, 6 times the x value. And the fyy, according to the calculation we did previously, that's a negative 8. That's a constant. So fxx times fyy minus fxy. Fxy, it is also calculated from the previous step. It's a 2, fyx the sine. So what I'm seeing here is this time the determinant, keep in mind, actually, yeah, I'm looking at this part. The determinant in this case, because this is negative times another negative, that tends to be far bigger. I say it's very safe to say far bigger than 4, right? So the determinant is positive. And then, according to the second derivative test, when the determinant is positive and the second order partial derivative it is negative, then we say we are having a local, actually, I believe this is local maximum, right? As I just said, the second order partial derivative is negative, which means the graph opening downward. So really, this should be a maxima. Maxima here. And the maximum value is, here, this is the maximum. Okay, the maximum value, it is the function value by plugging this ordered pair for x and y. and I just plug in all the numbers. Somewhat, I guess it's well, I guess you may want to use a calculator to figure out all the numbers. But anyway, as I'm saying, for me to save some time, I really did not do all the calculation. I did show my work. Okay, so this is local maximum. And this is the topic for section 4.7. Local maximums and the minimums for function of two variables. There is the second derivative test. Thank you for watching.